All right. So what I want to cover today is orthogonal matrices. Um, we skipped this. It's actually from I think it's a 6.2 handout. I've also included that info on the 7.2 handout. Um, so all the main info is on there, but some of this stuff will derive, some of it we're just going to kind of assume for now. So anyway, definition of an orthogonal matrix is that it's, let's see, how do I want to phrase this? An orthogonal matrix, let's say A, is an invertible one, and it has the property that A inverse is the same thing as A transpose. Now, what we're not proving right now, we'll prove this later if we have the time. There are three different ways. It turns out, so one way of thinking about it is just the pure definition of orthogonal matrix, which is what we just said. A inverse equals A transpose. Turns out you can use that to prove that the column vectors of A are all orthogonal to each other. And each column vector is a unit vector too. So magnitude 1. So, well, we'll do that in a minute. And since A inverse and since A transpose is also, I mean, if the column vectors are all orthogonal to each other, and you know that the inverse and the transpose are the same, then you could probably guess pretty quickly that if I just transpose everything, it's still going to be the same thing, which means that the row vectors of A are all orthogonal to each other. I'm just going to do this. And every row vector is a unit vector. Okay, so that's all written on the 7.2 handout. In a minute, I'll talk about why orthogonal matrices are actually useful, like why it's good to know that they're orthogonal. But first, let's do an example. Oh, yeah, so really, these three statements, they're all equivalent. So really, if you prove like number 2 instead, that's the same thing as assuming number 1. So if you got to prove something's an orthogonal matrix, prove any one of those three things. Okay, so let's try looking at an actual matrix here. So as an example, let's prove that A equals, and then I'm going to do a 3 by 3 here, 2/3, 2/3, 1/3, negative 2/3, 1/3, 2/3, and 1/3, negative 2/3, 2/3 is our matrix A. And we want to prove that A is an orthogonal matrix. Okay. And I want to prove it, well, you could prove it two ways. You could go for the inverse and then show that that's the same thing as the transpose. But what I'm going to do is I'm going to aim for number 2. Let's say the column vectors are all orthogonal to each other and every column vector is a unit vector. So what I'll do is I'll call this one right here U. I'll call this one V, or V, duh, and I'll call this one W. And so really in order to prove this, you want to show that U and V are orthogonal to each other, V and W are orthogonal to each other, and U and W are orthogonal to each other. So, well, let's just look at it. U dot V is going to be, let's see, 2/3 times 2/3 plus negative 2/3 times 1/3 plus 1/3 times negative 2/3. And if we add all that up, that's going to be 4/9 minus 2/9 minus 2 more ninths. So that's going to be 0. And therefore we can say U has to be orthogonal to V. Right, so we got that part done. And then if I do V dot W, well, you're going to end up with the same thing. If I do 2/3 times 1/3, you're still going to get 0 out of this thing. And if you don't, then something's wrong with the matrix in the first place. It's not going to be orthogonal. So here's V dot W, and this is 2/9, 2/9, and negative 4/9, so we get 0 again. So therefore V is orthogonal to W. And then we also have to check are U and W orthogonal, because it is possible that, you know, maybe U looks like this, V looks like this, and W looks like that, right? So in that case, W and V wouldn't be orthogonal too. So we got to prove that all three of them are orthogonal. So this one, let's see, U dot W would be 2/3 times 1/3 plus negative 2/3 times 2/3 plus 1/3 times 2/3, and then this one's also 0. So now we've got U is orthogonal to W. So we got the column vectors, whoa, are all orthogonal to each other. So that's half of what we're trying to prove. The other half is show that each column vector is also a unit vector. Okay, so let's just look at the magnitudes and show that they're all 1. So this one's going to be square root of 2/3 squared plus negative 2/3 squared plus 1/3 squared. So that's going to be square root of 4/9 plus another 4/9 plus 1/9. And so I'm going to get the square root of 9/9, which is 1. So that's good. And you can do the same thing. I'm not going to work all these out, but if you work this out, you're going to get 1 for that guy, and then you're going to get 1 for W also. So this says all column vectors are unit vectors. And since we have this property and this property, we can say A is an orthogonal matrix. Okay. Now, if you can use a calculator, sure, go ahead and just plug in A inverse, and then A transpose, you can just eyeball it and take a look. So, but the idea is kind of using these different ways of approaching it. So let's talk about why orthogonal matrices are important. So remember, every matrix I give you, you know, any matrix I give you, if you multiply it by a vector that represents a point, like x, y, z, you get some image point, x prime, y prime, z prime. And so this matrix transforms all of your points into new points. So if it's an orthogonal matrix, if this one's orthogonal, so I want to represent, first let me write this out. So if we think of it in terms of transformations, so let's see, I'll call this the x vector. Yeah, okay. So this is the function that I'm using, t of x, is the same thing as taking my orthogonal matrix and multiplying it by my x vector. This is A, this is x, this would be x prime over here. Then this right here, t, is called an orthogonal transformation. And the reason these things are useful are that just like rotations, they keep everything pretty much the same. All you did is spin the thing, but lengths stay the same. Like if you have two vectors and you know the angle between them, that angle between them stays the same. The distance between any 2 points, like if I've got this point, and then I rotate by 90 degrees, wherever they end up here, you know, this point and roughly in the same spot here. This one will end up about there. This one will end up about there. They're still the same distance apart, right? Those still end up being the same distance. So an orthogonal matrix is useful because it preserves three things. So orthogonal, whoop, orthogonal matrices, or actually let's say transformations, preserve three things. One thing that they preserve are lengths or norms. So that means that if I'm working in the original world, of just regular vectors u and v, the magnitude of u is going to be the same thing as when I plug it in and get my transformed version of that. These guys are going to be the same. The angles are going to be the same. So preserves angles. So that means that the angle between two vectors u and v is going to still be the same as the angle between t of u and t of v. So I've got my original vectors in whatever world I'm working in, and then I turn them into this transformed version. Whatever angle was between them originally, still between them. Last thing it preserves are distances. So if I have 2 points, P and Q, and I figure out what the distance between them is, that's the same thing as if I found the distance between R and S. And I know that looks vague, but P is the thing that gets mapped to R. Q gets mapped to S. The only reason that I can't just say like T of P and T of Q is because P and Q are considered coordinates here, not vectors. So really, you just replace them with the vector version, and you can still calculate everything the same way. Okay, let's see. I think that about does it for the stuff that I need to go through. Let me just double check here. Yeah, I think that's all good. Okay, so I'll post some homework on our agenda. Hopefully this stuff isn't too complicated. I think you guys can kind of piece together what you need out of it. There are going to be some orthogonal matrix problems for homework. You can do them during class. I think it'll be pretty quick to get through them. Since 4 people are already out on Kairos anyway, I'm not going to assign a ton. So, okay. I'll see you guys either Monday or Tuesday, whatever day is the first day that we meet next week. And we'll go over whatever you need on that day. Okay, I'll see you soon.